Hi everyone, today I'm very glad to introduce my paper published in PVIDB 2023. The title is Towards Efficient Index Construction and Approximate Nearest Neighbor Search in High-Dimensional Spaces. This is the outline of my presentation. I first describe the backgrounds. The problem we want to answer is high-dimensional nearest neighbor search. Given a set of points D in the RD, a query point Q, n search returns a point O star in the dataset D, where O star is the exact nearest neighbor of Q. Many real-world applications can be reduced as finding similar items in a high-dimensional dataset, such as web search, image classification, and so on. Hence, this problem is very important. However, the brute force method to this problem have a very high complexity, which is unaffordable. So we tend to answer the approximate nearest neighbor search. A popular version of approximate nearest neighbor search is called as C approximate nearest neighbor search, which is defined as follows. Given a set of points D in the RD, assume a query point Q and an approximation ratio C that is greater than 1, and let O star be the exact nearest neighbor of Q in the dataset D. A C approximate nearest neighbor query returns a point O such that the distance between Q and O is less than C times the distance between Q and O star. In this figure, the exact NN of Q is O2 and O14. And if these two, and then we can find any point among O2, O14, O12, O13, O6, and O7 as a result of 2 AM because their distance to Q is less than 2 times the distance between Q and O2. The methods to answer the AN search can be broadly divided into 4 categories. The first one is partitioning-based methods. Partitioning-based methods divide the data in the original space into several regular partitions and store them in the nodes. However, as the dimensionality D increases, the number of required nodes increase rapidly, and thus the approach is not adaptive for high-dimensional dataset. The second one is the hashing-based techniques, which partitions the data via several randomly chosen hash functions. Hashing-based approaches do not aim to find an exact end result. Instead, it ensures an approximate result with quantity guarantee. The third one is quantization-based methods, which cluster the data and represent them by some quantization values. These methods are not adaptive for high-dimensional datasets since the clustering result is not ideal as the dimensionality D becomes high. The last one is graph-based methods, such as HNSW. These methods answers the AN search via the proximity graph, which captures the nearest neighbor relationships among the dataset. Compared to the above methods, hashing-based methods and graph-based methods are two promising directions to solve high-dimensional AN search. Next, I describe one kind of hashing-based methods, ASH-based methods. The core idea of ASH-based methods is to answer AN search via the quantitative hashing, which maps the data and build the hashing index. The quantitative hashing satisfies the following conditions. If a function h is called as C or P1, P2 sensitive, then for any 2 points P and Q, if the distance between P and Q is less than R, then the probability that they have the same hash value will be greater than P1. If their distance is greater than CR, then the probability that they have the same hash value will be less than P2. In short, their collision probability grows as their distance. So the nearby points are more likely to be mapped into the same hash functions or hash buckets, which allows us to find the ANN of the QD points only in the box where it is located. ASH indexes are very easy to be built, and all ASH methods ensure a correct CAN result within a given query cost. However, they still have a limited query performance compared to other categories of graph ANN methods, since they are hard to find the exact NS. Moreover, since the hash functions are data independent, the query performance of SH-based methods varies greatly with the datasets. Next, I introduce the graph-based methods. Graph-based methods use the approximator proximity graph to answer AN query, and APG is defined as follows, which is a graph where V is the dataset D and E is some point pairs in the dataset. If the age 01, 02 is in the age set, which implies 02 is close to 01 in the dataset D. The figure shows an example of an APG. To conduct an AN search, we can adopt a greedy search. First, the search begins from a so-called entry point. For example, the point 021 in the figure. Then we compute the distance between the query point Q and each neighbor of the query point, i.e. 020, 019, and 018. Then then the closest neighbor will be selected as the next entry point. Such process repeats until we find a local minima, i.e. a point that is closer to the query point than any of these neighbors. Then we will return the local minima as the final result. Graph-based methods often achieve the much better query performance than SH-based methods. However, they all have much higher indexing time because we require to find the nearest neighbors for each point when building the index. So we can find the SH-based methods is easy to be built, but harder to achieve high query performance, while graph-based methods can achieve high query performance but have a much higher indexing time. So what if the graph meets SH? We can use SH framework to accelerate the index construction and use the APG to refine the query performance. Before introducing our method SH-APG, we see how to build an APG. A popular strategy is called as consecutive insertion. In this manner, we insert the point O in the graph IG one by one. We first find the ANS of O in the current graph index IG. Then, for each found ANS, we mutually connect it to Q as edges in the graph. So the building cost mainly comes from the query cost. This manner can find the high quality edges and facilitate the data updating because we can insert the new points easily when the data is updated. Our methods adopt this manner to build the graph index. How can we improve its performance with an SH framework? To find the benefit of SH framework. Let us see the query algorithm of other graph-based methods and a method SHAPG that has an SH framework. In previous methods, the entry point is chosen randomly. However, SHAPG can adopt the nearest neighbor found in the SH index as entry point, which can allow the search in the graph beginning from a closer point and faster to terminate. In addition, SH framework can filter out some unnecessary edges. In previous methods, we request to verify each neighbor of the entry point, which is time-consuming. But in SHAPG, only those neighbors that have a close distance in the hash space require to be verified. Finally, I report the experimental result. We compared SHAPG with 3 baselines on 8 datasets. We evaluate the indexing performance and the query performance of all algorithms. As for the indexing performance, SHAPG has a higher index size because it has an actual SH framework. However, it also has a higher quantity edge and a smaller index time. This indicator SH framework helps reduce the indexing cost. As for the query performance, SHAPG achieves the smaller query time to reach the same recall, which demonstrates SHAPG achieves a better trade-off between the query efficiency and the query accuracy. This is my presentation. Thanks for listening.